word in the title, but I hope you don't mind. Today I'll talk about complexity of polynomial families, and this is related to the Polynomial Szemerédi theorem. Let me start by discussing the classical mean ergodic theorem of von Neumann. So if X is an ergodic system, where for me a system during this talk is an invertible measure preserving dynamical system, and if F is an L infinity function, then the following sequence of averages converges in L2 to the integral of F. You can notice that the actual mean ergodic theorem holds under slightly weaker assumptions. However, during this talk, I will work in this setting. That's why I made slightly stronger assumptions than necessary. One question that we could ask here is what happens if we replace the n in the exponent by some polynomial in n, such as, for instance, 2n or n squared. And in general, I'll call a polynomial integral if it has integer coefficients and zero constant terms. In this case, the following sequence of averages also converges in L2, although the limit is a bit harder to describe explicitly. So during this talk, I will focus on discussing the properties of so-called multiple ergodic averages. These are averages of this form. So here I'm averaging over a product of functions, where on each function I'm acting by a polynomial iterate of the same transformation T. One of the main results about the convergence of these averages has been proved by Host-Kra in 2005. They showed that if the system is ergodic and if the functions are infinity, and if I take distinct integral polynomials, then the following sequence converges in L2. We know from functional analysis that strong convergence of this implies weak convergence, and hence we have the following corollary. So if we take an ergodic system and L infinity functions and distinct integral polynomials, then the following sequence of averages of integrals also converges. And one case in which this is interesting is if we take all the functions to be an indicator function of some measurable set. In this case, we get an average of the measure of this intersection. And by the corollary, this sequence also converges. So you might ask, why do we care about the convergence of these objects? Why would we want to study them at all? And the reason is because they appear in the Polynomial Szemerédi theorem of Bergelson and Leibman. This theorem exists in two versions, an ergodic one and a combinatorial one. I'll discuss both of them, starting with the ergodic version. So the ergodic version goes as follows. If I have distinct integral polynomials, an ergodic system, and the set A of positive measure, then the following limit exists and is positive. I'm quoting here both Bergelson and Leibman and Host-Kra, because in the original result of Bergelson and Leibman, it was only shown that the limit is positive. And it was only in 2005 when Host-Kra showed that the sequence actually converges, so that the limit becomes the limit. And as a corollary of this result, it follows that there exists some positive n for which the following intersection has positive measure. And in particular, it must be the case that there exists some element x for which all these points are contained in the set A. So this was the ergodic version. Let me now do the combinatorial version. So here we again have distinct integral polynomials. The combinatorial version of the same theorem says that each dense subset of natural numbers contains a polynomial progression of the form given on the board, where here n is again non-zero. So as an example of this, we have that each dense subset of natural numbers contains a progression, a configuration of the form x plus n squared for non-zero n. And let me perhaps clarify what dense means. So for me, a subset of natural number is dense if it has a positive upper density, which means that it occupies a positive proportion of natural numbers. And more formally, this is given by the following limb sup here. Otherwise, we call the subset sparse. So for instance, the set of even natural numbers is dense with density 1/2, because half of natural numbers are even, whereas the set of primes is sparse, because from the prime number theorem, we know that the number of primes up to n grows like n over log n. So the proportion of primes will converge to 0 as n goes to infinity. Let me perhaps add that the combinatorial version follows from the ergodic version by the so-called Furstenberg correspondence principle, which has been proved by Furstenberg in his proof of the Szemerédi theorem in the 1970s. So this brings us to the following question. Can we say anything more specific about the L2 limit of such sequences? And this is the question on which I will focus today. And the answer is yes, of course, otherwise we wouldn't be here sitting and listening to this talk. But to tell you what we can say, what more we can say, we need to define the notion of a factor. There are at least 3 definitions of a factor. I'll state 2 of them. The simplest one is this. So a factor of a system is simply a t-invariant subsigma algebra of the system. Equivalently, a factor can be defined as a separate system y together with a factor map pi from x to y, which satisfies some natural properties. And instead of explaining in words what these properties are, I think it will be more instructive to just give an example of a factor. So if I take S to be a translation by an element A of one-dimensional torus, then this is the factor of the second system given here. So the second system here is a skew-shift transformation on a 2-dimensional torus. And if I define the map pi from the 2-dimensional torus to the 1-dimensional torus by projecting onto the first coordinate, then you can observe that under this map, the transformation T reduces to the transformation S. And this is what it means for S to be a factor of the system T. And why do we care about factors here? So in their proof of this result that I stated before, Host-Kra basically showed that if we have a sequence of averages like this, the limit remains unchanged if we project all the functions onto some well-structured factor y. So this factor has to be big enough for these 2 limits to be equal. However, it has to be small enough for it to possess some extra structure that we can then use to show that the second limit converges. And that's the idea behind Host-Kra's proof. So right now, I would like to talk a bit more about what these factors are. So in their seminal work from 2005, Host-Kra constructed a tower of factors for each ergodic system. And I'll denote these factors as Z0, Z1, Z2, etc. And henceforth, I will call them Host-Kra factors. These factors satisfy the following important property, namely that if I have an ergodic system and infinity functions and distinct integral polynomials, then there exists some number S such that the following L2 limits agree, meaning that the first limit remains unchanged if we project every function onto the ZS factor. And the important thing here is that the number Z depends only on the polynomials, but it does not depend on either of the system or the functions that we choose. So what are these Host-Kra factors? I will not give you a definition of these factors because it would occupy a better portion of the talk to even define and explain what the definition means. Instead, I will focus on some essential properties of these factors that are used in the proof that the limit actually exists. So the smallest of these factors, the Z0 factor, is simply the sigma algebra of T invariant sets. The second factor, the Z1 factor, is the so-called Kronecker factor. So it's the maximal factor of the system. I'm assuming ergodicity here. Yeah.
Ergodicity is assumed.
Yeah. I assume ergodicity here throughout this talk. Yeah. So the factor Z1 is the Kronecker factor. So it's the maximal factor of the system X, such that the following system with the sigma algebra replaced by Z1 is isomorphic to a rotation on the compact abelian Lie group. And then things get more complicated. So more generally, for higher values of S, the factor ZS is an inverse limit of S-step nilsystems. So what are these S-step nilsystems? The space here is an S-step nil manifold. So it's an S-step nilpotent Lie group quotiented out by a co-compact lattice. Then we have the Borel sigma algebra, the Haar measure, and the transformation here is a left multiplication map for some element G of the group. We call such maps nil rotations. So these are nilsystems. And because it sounds a bit complicated, I'll illustrate these definitions with some examples. So for the one-step nil system, we can just take a rotation on a torus. So here you have a translation on a torus. So here you have a translation by the element A, and this defines a one-step nil system because torus is a one-step nil manifold. For a two-step nil system, I'll take the following skew-shift map as an example. And it's not clear from this description why this would be a nil system. However, it turns out that this system can be realized as follows. So if we take the group G to be the group of the matrices given here, and if we quotient it out by the lattice gamma, then it turns out that the transformation T given above corresponds to the left multiplication by an element G listed in one of the lines there. So we can check that if I act by T on any matrix like this, where T is defined here as the left multiplication by G. So if I left multiply by G an arbitrary matrix of this quotient G mod gamma, then in coordinates, this acts precisely like the map T that I gave before. Okay, and that's why the system is an example of a two-step nil system. So it's a late afternoon talk, so I thought that you might use some short break to help you refocus and wake up a bit. This photo is from Tatry in mountains. These are beautiful mountains. If you haven't been there, I highly recommend. It was taken three years ago. This is from the highest peak on the Polish side of West Tatry. Okay, end of break. Let's come back to math. Starorobociański. Yeah, and Starorobociański is on the border. So right now I'll discuss the main question that I have been studying and for which I'll present results today. So for the rest of the talk, I'll assume that T is not just ergodic, but that it's totally ergodic, meaning that every iterate of T is by itself ergodic. And recall from what I told you before that these Host-Kra factors define a tower of factors, meaning that Zs is a factor of Zs plus 1 for each natural number S. Given that, we want to know the following. Let's fix distinct integral polynomials, P1 through Pk. We want to know what's the smallest S such that for every totally ergodic system and every L infinity function, the factor Zs satisfies the following equation. So what this equation once again tells us is that the original limit remains preserved by projecting all the functions onto the Host-Kra factor Zs. And if Zs satisfies this property, then we say that Zs is a characteristic factor for this polynomial family. And the smallest S for which this is the case is called the complexity of the polynomial family P. Hence the word complexity in the title of the talk. So there have been several results in the direction described above. I'll just focus on one of them. In 2005, Frantzikakis and Kra answered the question given on the previous slide for families of linearly independent polynomials. So the most natural example of such families are just subsequent powers of n. So n squared, n cubed, etc. And what they showed is that the factor Z0 is characteristic for this family, which once again means that the following L2 limits are the same. And why is this interesting? So by definition, the factor Z0 is the sigma algebra of T invariant sets. Hence, if we perform some algebraic manipulations, we will see that this expression here just equals the integral of the function fi over the set x. And therefore, combining this with the theorem listed above, it turns out that the limit of the sequence of averages is just the product of integrals of the functions f1 through fk. So here we're getting a very nice formula for what the limit is. And I hope this provides an extra motivation for you for study and for me, of course, for studying these questions and I hope it justifies why this problem in itself is quite interesting. So before I state my own results, I'll give several simplifications that will help motivate the results later on. As I explained before, it's enough to study weak convergence. And so we want to answer the following question, which is a variant of the previous question. So let's fix distinct integral polynomials. And we want to know what's the smallest s such that for every totally ergodic system and every L infinity functions, the factor zs satisfies the following equation. So here we're no longer talking about L2 limits. Here we have just limits of numbers because we replace functions by integrals. So that's the first simplification. There is another simplification that we can make, namely using the fact that t is measure preserving, we can rewrite the integral as follows. So we can introduce an mth power of the transformation t for each of the functions appearing in the integral. And as a consequence, this allows us to replace the first limit by the second limit listed at the bottom of the slide. So what we have done here is we have introduced an averaging parameter m. And this parameter turns out to simplify things quite a lot in computations. So before I present my own results, I'll have to talk a bit about algebraic relations, because it turns out that to answer the question listed on the previous slides, it's essential to understand the algebraic relations satisfied by the polynomials that belong to the family. So for me, an algebraic relation of degree s satisfied by this family is a relation of the form given here, where q0 through qk are polynomials, the highest degree of which is s. Okay, so that's an algebraic relation of degree s. And to illustrate this with a specific example, let's look at two families. First, the family n squared, n plus n squared. So this family satisfies one linear relation up to scaling, of course, and it's the relation given here. Let's now have a look at another example, the family n2 and n squared. This family satisfies two linearly independent relations. One is linear and the other is quadratic. And of course, it also satisfies any linear combination of these relations. So right now, I want to explain how these algebraic relations fit into the picture. So how are they related to the complexity of families of polynomials? And the connection comes through this conjecture. So let P1 through Pk be distinct integral polynomials. Then the conjecture here is saying that the factor Zs is characteristic for this family P, if and only if the family satisfies no algebraic relation of degree s plus 1 or higher. Now, this sounds very abstract when you see it like this. So once more, it's easier to understand it if I give you some examples. For instance, if we look at the family n squared, n plus n squared, I showed you before that it satisfies exactly this one relation. And what the conjecture is saying in this case is that the factor z1 is characteristic for this family. For the second family that I discussed, so n2 and n squared, the highest degree relation that it satisfies is quadratic. It's the relation given at the bottom of the slide. So what the conjecture is saying is that the factor z2 is characteristic for this family. From what I told you so far, there is no clear indication why algebraic relations would even be useful to study this question. There's no reason why they would even appear in this question. So in this slide, I want to explain where the connection comes from. So I'll illustrate it with a simple example. Let T be the following skew shift map on a two-dimensional torus. And by taking A to be an irrational number, this transformation becomes ergodic. Let's see first what happens if we take the mth iterate of this map. So if we take the mth iterate, then you can see that the first coordinate is linear in M, is a linear polynomial in M, while the second coordinate is a quadratic polynomial in M. Okay. If I replace M in the exponent by M plus Pn for some polynomial P, then once again, in the first coordinate, I'm getting a linear polynomial in M plus Pn, whereas in the second coordinate, I'm getting a quadratic polynomial in m plus pn. Okay. So let's now see what happens if we right now look at the pointwise limit of the following expression at the point 0, 0. Okay, and the functions are continuous. So it's all nice here. So by Weyl's equidistribution theorem, it turns out that understanding this limit is equivalent to understanding the distribution of the following sequence inside the 6-dimensional torus. That's just a very explicit application of Weyl's equidistribution theorem. And where do these terms come from? So if I take Tm at 0, 0, then by looking at this expression here, you see that in the first entry, I just get am, while in the second entry, I get am squared, hence the first two terms here. If I take t to m plus pn at 0, 0, then again, in the first coordinate, I get a times m plus pn, while in the second coordinate, I get a times m plus pn squared, and hence the next two entries here. And in a similar way, we can obtain the last two entries. Okay, so we need to understand, to understand the distribution of this tuple of this sequence inside the 6-dimensional torus, we have to understand the linear relations between these 6 entries. And if you look carefully at what these entries are, it turns out that to understand the linear relations between these 6 entries, we just have to understand the quadratic relations between 3 polynomials, m plus pn, and m plus qn. So that's where the algebraic relations come from. They are a sort of abstraction that have to be taken care of. And the conjecture that I stated on one of the previous slides says that these are the only abstractions that one has to take into consideration. To state my result, I need to discuss one special family of algebraic relations, and these are homogeneous relations. So a homogeneous relation of degree S is simply a relation of the following form. So it's a linear relation between the S powers of the polynomials m plus p1n, all the way up to m plus pkn. And a family of polynomials will be called homogeneous if all the relations that it satisfies can be written down as sums of homogeneous relations. So for instance, the family n squared, n plus 2n squared satisfies only one relation up to scaling. This relation is linear, and all linear relations are homogeneous by definition. That's why this family is homogeneous, okay? But let's now look at another example. So let's look at n, 2n, n squared. I showed you before that it satisfies the following relation, and I'm claiming that it's non-homogeneous. Why is this so? It's for two reasons. So first, the polynomial in M is not it's not a monomial. It's not a homogeneous polynomial. And second, whereas the polynomial in M, m plus n, and m plus 2n, they are all quadratic, the polynomial in m plus n squared is linear. And so this relation is not of the form given at the top. So it's not homogeneous. Not only is it not homogeneous, but also it cannot be written down as a sum of homogeneous relations. And that's, by the definition, precisely what it means for this family not to be homogeneous. Okay? So we have one homogeneous and one non-homogeneous family here. And having defined this concept of homogeneity, I can finally state my result. So let me recall the conjecture. The conjecture is saying that the factor ZS is characteristic for a family, even only if this family satisfies no algebraic relation of degree S plus 1 or higher. And what I was able to show is that this conjecture holds for all homogeneous families P. And again, this is very abstract. Let's look at some examples. I have already discussed this family a few times. I showed you that it's a homogeneous family satisfying only this linear relation. So by the theorem, the factor Z1, so the Kronecker factor, is characteristic for this family. Now, this example has already been proved before by Nikos Frantzikinakis. However, the following example is new. So this family I have not discussed before. It's n, 2n, n cubed, 2n cubed. However, you can hopefully see quite easily that it satisfies only two homogeneous relations. And these are the linear relations given at the bottom. And so since it only satisfies linear relations, it's homogeneous by definition. And so by that theorem, the Kronecker factor Z1 is characteristic for this family. And these two examples can be extrapolated. So if we have a family of polynomials that only satisfy linear relations of this form, then these families are homogeneous, okay? Because linear relations are always homogeneous. So if I have a family satisfying only linear relations, but no quadratic or higher order relations, then by the theorem, the Kronecker factor Z1 is characteristic for this family. And let me recall once again what this means. This means that the L2 limit of the first average over there equals to the L2 limit of the second average given below. And this works for every totally ergodic system and every L infinity functions. In fact, in this case, this actually works for every ergodic system, but I wanted to be consistent in the notation, which is why I only wrote totally ergodic. So this particular corollary has been known before in the case k less than equal to 3. So for families of length 3 or less, and it was known due to Nikos Vranskinakis. However, the longer case was unknown, and this corollary proves it for all k. And I'll discuss very briefly the ideas in the proof. So first, we use Host-Kra's result to replace the original average by the average where all the functions are z's measurable. For some s, Host-Kra's result doesn't tell us what the s is. It only tells us that there exists some s for which we can project the functions onto the z's factor. Then we use the structure theory of Host-Kra factors to approximate the system arbitrarily well by a totally ergodic Nil system. And this puts us in the realm of equidistribution theory of polynomial sequences on Nil manifolds. So the last thing that one has to do is to show is for each ergodic element G of the group G, we want to find the closure of the sequence given here inside the Nil manifold given here as well. And the reason why it's enough to find the closure is because by a result of, I think, Leibman, under some conditions on G, this sequence is equidistributed on the closure inside this larger space here. And it's this last step here, the step of finding the closure, where homogeneity of the algebraic relations really comes into play. Because if the relations are homogeneous, then we can find a very explicit, very nice expression for what the closure is. Whereas the moment we get a non-homogeneous relation or a non-homogeneous family, this becomes much more complicated. And at the end, I would like very briefly to discuss two applications of this result. And I'll discuss them for the family n, 2n, n cubed, 2n cubed. So here we have the following result. If I have a totally ergodic system and L infinity functions, then the following two limits are equal. The reason why this result is nice is because, well, the original expression here may be a bit hard to evaluate. We have transformation acting with different powers. We have transformation with linear powers and with cubic powers. Whereas in the second expression, we are able to replace the cubic terms by a separate variable. So this is one sort of application of the complexity results that we can obtain. We can get simpler expressions for these limits. The second application is related to recurrence problems. So there is this old result of Khintchine that for every epsilon, the following inequality holds for infinitely many n. So for infinitely many n, this intersection has measure almost equal to the measure of A squared. And we can extend this to for larger intersections. So so one can show that for knowing the complexity of this family, one can show that for every ergodic system and every measurable set of positive measure, and for every epsilon greater than 0, there are infinitely many natural numbers n, such that the following inequality also holds. In fact, not only are there infinitely many natural numbers for which this holds, but also the set of such numbers is synthetic, meaning it has bounded gaps. So it's a very large subset of natural numbers. That's it. Thank you. And wszystkiego najlepszego. So for an arbitrary system, it doesn't tell me that much, but knowing that, that for instance, the Kronecker factor is characteristic for a certain family allows me to get simpler expressions for the limit in some cases. However, in general, I can't get as nice a result as Franzkinakis and Kra obtained before. So product of integrals, this is not attainable here. Yeah. No. Mm-hmm. Maybe I did not pursue in this direction, to be honest. Yeah, but yeah. So I'm not sure. Yeah. Sorry, I can't hear. Yeah.
So I think you may need some Diophantine conditions for equidistribution. Am I right?
So what I was using here was not just Leibman's equidistribution theorem, but the quantitative version of this theorem by Green and Tao.
Yes.
And in their work, they define a special family of polynomial sequences that they call irrational polynomial sequences. So this is some sort of Diophantine condition, but it appears sort of indirectly. So I don't have to work with Diophantine properties explicitly because all the Diophantine stuff has been sorted out by the theorem of Green and Tao that I'm applying.
Yes.
Yeah.
Okay, thank you.
Okay, other questions? If not, let us thank the speaker again.